Okie doke, welcome to week 3, part 1. In this part, we're going to take a look at the idea of iterables and iterators so that we'll be able to see how it is if you define a class of your own, you can actually make your class an iterable by defining this thing called, or defining these things called iterators. Previously, we said that an iterable is something that you can loop through using a for loop. And that's true, but it's maybe not the best description in the world because it just sort of begs the question, well, okay, fine. How do for loops work in this case? Okay, so the way a for loop works is to make use of two methods that the underlying iterable object or class has to provide. The first of these methods is iter, which returns an iterator type of object that we can use to access the object that we're iterating through. The second method is called next. Next actually takes an iterator as its argument and returns to us the next value in that iterable. So let's take a look at some examples here. Here we have a for loop, m, which we've defined to contain three integer values, 2, 5, and 1. And we're using a for loop with this variable v to step through the items in M and display those items on the screen with print one at a time. So the first time through the loop, a value of 2 is retrieved from M. That's the first value in M, and that becomes the value of V, and that's printed. The second time through the loop, V gets set to 5 and is printed, and the third and final time through, V gets set to 1 and printed. But how does this actually work under the covers? Well, under the covers, what's going on is that when the for loop is executed, internally the for loop invokes this iter function on the list object M. And the iter function returns an iterator object, which I'm uncleverly calling M iterator or MIT. And then each time the for loop steps through to the next value, literally it uses this method next on the iterator, which returns the next value from the list. And I can do this interactively, so let me pull up my Python shell so that we can step through this. Okay, so I'm going to create m equal to, or referring to, this list of three int values, 2, 5, and 1. And I'm going to say for v in m, print v. And we've seen how this works. But as an alternative, I can sort of unwind what the for loop is doing internally. I can say m iterator gets an iter object from, or referring to, the list m. All right, so MIT is now my m iterator, my iterator through m. And each time I call next with that iterator, MIT, I'm going to get back the next available value from m. All right, so the first time I call next with MIT, I get a 2. The next time I get a 5. The next time I get a 1. How do I know that I'm at the end? Well, it turns out that when you invoke next on an iterator that has already exhausted the values in your iterable, what happens is you get something called a stop iteration exception. And so we can use iter to create our iterable, and then we can use next until we bump into this stop iteration exception, and then we will know that the iterator has reached as far as it can. I can simply recreate the iterator by saying MIT gets iter m again, and then I can use my iterator again to step through these values. All right, so I get 3 values, and then when I ask for the 4th, I get my stop iteration exception again. Okay. And in fact, every time I call next on an iterator every time I call next on this iterator, once it has reached the end of the values that the object contains, I will just always get back stop iteration from that point, or I will get a stop iteration exception. Okie doke. So, rather than just hand waving and saying that an iterable is something that you can use with a for loop, an equivalent way of saying the same thing is that an iterable is some kind of object that has an iter method that returns an iterable object, and that also provides a next method which, given that iterable object, will return the next value. Now, of course, we have to assume that the iter function and the next function are defined to are defined to work in a reasonable way. If we define iter to return the value 5, and if we define next to call the print function, those are, technically we will have defined the iter function and we will have defined the next function, but those are ludicrous, pointless definitions. Now, because we won't know that we have reached the end of the sequence or the collection of, I need to be careful not to use the word sequence, so forget I said the word sequence. A sequence is an entirely different thing, which we'll talk about next week. So we'll know that we have reached the end of the values contained in our collection when we hit this exception. And in order to prevent our program from crashing when we hit the exception, recall that we can use a try block containing statements that we fear might generate an exception, and we can use an except block to handle any exception that does occur. Now, this approach that we've talked about before handles any kind of exception at all. And so that will handle exceptions not only including stop iteration, but also including divide by 0 and index out of range and bad data type and blah, 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 blah. So we need a more sophisticated mechanism than this brute force try except we've seen before, because we want to be able to handle specific kinds of exceptions. And in fact, once we know how to handle specific kinds of exceptions, it turns out we can set up multiple except blocks at the bottom of a try block to handle these different kinds of exceptions. Here's how that looks. Okay, so we're going to have one try block containing statements that we fear might fail. And if one of these exceptions might be a stop iteration because we have hit the end of the values contained in some collection object that we're stepping through, we can specify how to handle that stop iteration by having an except block labeled with stop iteration. Okay, and we can have other kinds of explicitly labeled exceptions before or after the stop iteration. So if we fear that an index error might occur, we can set up an except block to specifically handle that type of exception. If we fear that a type error might occur, for example, if we accidentally use a string in a context where a floating point number is required, that might generate a type error, or our stop exception error, or various other kinds of errors. Now, if some error occurs in our try block that we have not got an explicit type of exception set up for, we can have an unlabeled except at the end of the whole list of labeled exceptions, and that will handle any other kind of exception that occurred that wasn't handled by one of our earlier labeled ones. Also, it turns out, and this is a new idea, it's entirely possible that in the try block, no exception occurs. And I'll be honest, I'm not a big fan of this notation, because I assume that, I'm trained to assume that an else has to be preceded by an if. But in this particular case, a try block that ends with an else, the else specifies what statements should be executed if there are no exceptions. Okay, so we're going to try to do some statements that we fear might cause an exception. If an exception occurs and that exception is an index error, we can handle it. On the other hand, if that exception is a type error, we can handle it. On the other hand, if that exception is a stop iteration error, we can handle it, etc., etc., etc. Otherwise, if the exception is some kind of exception that we didn't have a specific way of handling, we'll handle this unlabeled exception. And otherwise, finally, if no exception did actually occur, we'll perform these statements that are within the else. Okay. Another little tool that we need to know about in order to successfully implement iter and next inside of a class that we've defined is a break statement. Break, when you use it within a loop, a while loop or a for loop, simply causes the loop to terminate without going on to the next step. And here's a specific example. Now let me do this interactively in my shell so that you can see what's going on. Okay, let me do this interactively in my shell so you can see what's going on. Here's my shell, and I'm going to say for v in, and here I have a literal list typed in, 3, 2, 9, 1, 5. And I'm saying print the value of v, and then if, oh, I don't need parentheses here. I guess I'm, think I'm, I just noticed that this is actually a syntax error. I've written a C++ style if test rather than a Python style if test. So I'm going to correct that here. I'm going to say if v is greater than 5, break. Okay, so the upshot when we run this is v is going to get set one value at a time to these values in this list, 3, 2, 9, 1, 5. So v is going to be set to 3. I'll print 3 as the value of v. And then I'm testing, is 3 greater than 5? Since 3 is not greater than 5, I go back up to the next iteration of the loop. V gets set to 2. 2 gets printed. 2 greater than 5 is false. So again, I go back up to the next iteration in the loop. V gets set to 9. 9 is printed. Now, 9 is greater than 5, so at this point we break, which means that we just blast our way out of the loop to whatever statements, whatever statement comes after the for loop. So the upshot when I actually run this is 3 gets printed and I don't break. 2 gets printed and I don't break. 9 gets printed and I break and the loop is over. Okay, so now that we know about handling labeled specific kinds of exceptions, and we also know about break, we can take a look at the full-blown code that we need in order to give in order to get our next and iter functions to work. Okay, so first of all, we're going to take a look at the for loop that we've already discussed. The for loop contains within it all this knowledge about exception handling and stop iteration and blah, blah, blah. And here, as we saw, if we say for v in m print v, that simply steps through and displays the values in m. All right, and let's remind ourselves, m is a list containing 2, 5, and 1. And if I say for v in m, print v, it displays 2, 5, and 1. Now, internally, the way the for loop is implemented, in effect, is to use a while loop, like so. Actually, I want that on my other slide, so let me put slide 11 over here. Whoop, too far, too far. Here we go. And let me put back up my, oops. And let me put back up my interactive shell. All right, so I've just shown you for v and m, print v, and we see that it displays 2, 5, and 1. Now, this is equivalent to creating an iterator for m. All right, so I'm creating an iterator for m that I'm calling m_iterator, or MIT. And while true, okay, notice that this is an infinite loop, except, lucky for us, it has a break in it, which will break the infinite loop, we certainly hope. And what we're going to say is try to get the next value that the MIT iterator refers to. Now, that might fail. So if it fails, and we get our stop iteration exception, then we're done in the loop. There's nothing more to do, and we simply break out of the loop. Otherwise, if we did not get any exception, all right, so here's the else that's at the bottom of the try block and all of its various exceptions. In this case, we've got a try block. We've only got one exception. And then else, we're going to say print v. And so this code does the same thing as our for loop. We're setting up an iterator for m, and then until we hit the stop iteration exception, that is, while true, we're going to see whether next returns us a value or generates a stop iteration exception. If next returns us a value so that there's no exception, we'll just drop down to the else part and display that value. Otherwise, if next does generate a stop exception, we're done and we break out of this while loop. So, what have we done? All right. we have talked about how to use iter to get an iterator for stepping through a collection of values. We've talked about using next on that iterator to get the next value available from some collection of values. We've seen that next might fail and produce a stop iteration exception, in which case we don't want to do any more processing. Otherwise, we'll go ahead and process that value that we got, and we'll go up and try to get the next value. So this for loop is simply a much more convenient way of writing this while loop using the iter method and the next method. So what? Well, the so what is that if we have got a class that we want to be able to step through the item values that are contained within that class, if we define iter and next for our class, then the for loop will magically work for our class. And so that's what we want to do next. Let me get my... There we go. So what we're going to do now is to create a brand new class called tuplist. And this is going to be a list-like class. That is, we're going to be able to append values, we're going to be able to insert values, we're going to be able to look up an item using a subscript, we're going to be able to clear the list, the tuplist. We're going to be able to do all of the things that we can do with lists, but we're going to build this tuplist class using tuples as our internal representation for tuplists. Okay? All right. Now I'm going to confess that this is a really stupid idea in real life because we already have list as a built-in collection type, and we know lists are iterable and mutable and have a whole lot of capabilities the tuples don't have. So what we're doing here is we're using a restricted class, tuple, to implement a less restricted class, simulating lists. So this is a dumb and slow and clumsy thing to do. But the reason that we're doing it is so that we can demonstrate how you would define an iter method and how you would define a next method for your class, which presumably is not as stupid as this one. All right, so we won't have that much code to write, and it's just for demonstration purposes. All right, so here's our tuplist class, and we know that we're going to have a dunder init function for our tuplist class. We're also going to have a stir, a dunder stir function for our tuplist class so that we can print out the value of a tuplist object. Then we have all of our usual methods that we have for lists. We're going to have append, we're going to have insert, we're going to have count, we're going to have sort, we're going to have reverse, we're going to have all of these facilities for allowing a tuplist to be used as though it were an ordinary list. Okay? However, I don't actually want to implement all of those things. So, so I'm going to be content just to implement append and leave it to you as an exercise, which you don't actually have to do, to implement insert and to implement reverse and to implement sort and to implement count and all these other things. All right? So we're just going to do the minimum we have to, init, stir, and one example method, which is append. Okay, so how do we build a tuplist in our dunder init function? Well, we're going to take some iterable argument. That iterable argument might be a list, it might be a string, it might be a tuple, it might be a set, or it might be some other kind of iterable, it might be a range. And we're going to use the tuple conversion function to convert whatever that iterable is into a tuple. And that is going to then be stored in our underscore vals private variable. In order to convert the tuplist into a string, well, we're simply going to convert our vals, our underscore vals tuple, to a string, and we're going to prefix tuplist in front of that string, just so that we can tell that this is these are the values in a tuplist rather than the values in an ordinary tuple. Append takes a single value as its argument, just like the list append function does, and simply puts that new value at the end of the tuplist. We've seen this silly trick that we can do. Technically, remember that a tuple is not, it is iterable. A tuple is not mutable. A tuple is an immutable type. But we can sort of fake it by saying, let's set vals to pluskets of this additional value that we want to add as a tuple. Recall that, let me pull up my shell again. Recall that if I have a tuple vals containing a tuple built from a string, all right, so vals now contains or refers to a tuple built from a string. I can say vals pluskets some character in a tuple, and this is actually processed as vals gets vals plus that tuple. So the trick we're using here is that we're not directly modifying the existing underscore vals tuple. What we're doing is we're taking the existing underscore vals tuple, we're appending another tuple to that tuple, and then we're reusing the name underscore vals to refer to that new tuple. All right, so it sort of vaguely seems like we're changing underscore vals, but we're actually not. We're actually changing what underscore vals the variable name refers to. All right, so that's our implementation of our append method. And then we could do similar trickery if we wanted to implement insert, and we could do similar trickery if we wanted to implement, well, actually count would be, easy to implement. Reverse would be somewhat tricky to implement. Sort would be somewhat tricky to implement, but we could get all of those other things implemented. Now that we have a basic understanding of how this tuplist class is implemented, let's take a look at how we can define our iter method and our next method. Well, our iter method can simply set up some kind of private index variable to start from 0, because we know here we're taking advantage of our understanding of how the tuple data type works. We know that the tuple data type stores values in ascending indexes, starting from index 0 and going up through n-1 if there are n values in this tuple. So we're going to start our index at 0. That's what our iterator, that's what our iter method does. And then, as a return value, the iter function is simply returning a reference to the current tuplist object. All right, so each tuplist object that we create is going to have its own iterator. If I say tuplist TL1, tuplist TL2, tuplist TL3, each of these things, TL1, TL2, TL3, is going to have its own iterator. Then, the next method needs to return the next value contained within the tuplist object from the underlying tuple that contains the values. Well, and this is not efficient. I'm not pretending that any of this is efficient. But what we can do to implement dunder next is to test whether the index value for the current tuplist object is less than the length of the tuple containing all the values, Okay, remember that dunder vals is our tuple containing all the values. If the index is within bounds, then we can, as our return value, we can simply save the value from the tuple, the internal tuple that's at that index. We're also going to want to increment our index before we return the current value. And the reason that we increment the index is so that the next time we call next, we'll get the sub1 item instead of the sub0 item. And then the third time we call next, we'll get the sub2 item. The fourth time we call next, we'll get the sub3 item, etc. Now, if the index that we have is beyond the end of the tuple, well, that means that we've run out of values, and the way we generate an exception from within our code here is to raise that exception. All right, so when we run out of values, when there are no more values that we can return from next, we raise stop iteration. And therefore, anybody who invokes this next method will receive this stop iteration exception. Let's take a look at this program in our in an actual Python file. Okay, so here's the actual Python file. It's tuplist.py, and we have init and stir and append. All right, every class has to have init, every class has to have stir, and because we're trying to simulate how lists behave, we have defined one list method, which is append. And we could define all the other ones. We're also then defining, for our tuplist class, dunder iter that we can use to create an iterator object for ourselves, and dunder next, which operates on that iterator object and does one of two things. It either gives us back the next value from the underlying tuple containing our values, or it raises a stop iteration exception. I claim that because we have defined dunder iter and dunder next, that for loops work. And let's see if that's true. So here's our test code. I claim, and here's our test code. Notice that we're checking dunder name against the string dunder main. So if we are executing the tuplist.py file, we're going to create a tuplist containing 2, 5, and 11, and we're going to try to use a for loop to step through those values. Now, if our iter function and our next function are correctly defined, this for loop should work. All right, so let's test this thing and see whether that's true. And then I'm also going to do an append. So I'm going to append 9 after the 2, 5, and 11. I'm going to print the modified TL1, which will invoke the dunder stir method. And then I'm going to use next. Oh, I'm sorry. Then I'm going to create a new iterable for that TL1 object and use next 4 times to get the subsequent values starting from the initial value from there. Sorry. All right. So F5. Let me actually move over the output so that we can see the code and the output at the same time. Okay, so I've got my dunder init and my dunder stir and my append. Dunder init we always need, dunder stir we always need. Append is the one and only list simulation function that I bothered to define. Then I have dunder iter and dunder next. Dunder iter will get called when I use the iter function. Dunder next will get called when I call the next function. Dunder iter sets an index to the beginning of the internal tuple that contains the values. Dunder next verifies that we're within bounds. If we are within bounds, we return a value having incremented our index. If we're not within bound, we raise stop iteration. And so the first thing that happens in this test code is that we create a tuple list with 3 values, 2, 5, and 11, and then we use a for loop to display those values. So the for loop works. So the for loop works on our tuple list object TL1, which means that we must have defined iter and next in some appropriate way. Okay, now when I do the TL1.append and then print TL1, print is automatically going to convert TL1 to a stir using the dunder stir method. And what that does is to print out the literal text tuple list followed by the tuple representation of the values stored in the tuple list. Well, I initially had just 2, 5, and 11, and now I've appended 9, and so my output is correct. My tuple list following the append is tuple list of 2, 5, 11, and 9. I define an iter object, TL iterator1, TLIT1, to the beginning of TL1, and then I call next 4 times to display the 4 values. So 2, then 5, then 11, then 9. If I attempted at this point, and notice that in my example code I've commented this out, but if I attempt now to call next again on TL iterator 1, I will get my stop iteration error. And I'll always get my stop iteration error now that I'm at the end of the list. Remember that the for loop for, I don't know, I'll use a different variable name, for k in TL1, print k, and let's set the end equal to space so that we can get these all on one line. All right, so now I have these values on one line, 2, 5, 11, and 9. The for loop did create an iterator that it used internally. So what I've done here with the for loop is equivalent to saying TLIT2 gets iterator on TL1, while true, try to get the next value from the iterator. If that doesn't work and generates a stop iteration exception, I will break. Otherwise, I will type Python code now instead of C code. Otherwise, I will print the value. Oh, I see. I used I used an equality test here instead of an assignment. So let's try this again. TLIT2 gets iter TL1. Moment of panic there. While true, try v gets next. Come on, next. TLIT2. If an exception, a stop iteration occurs, I will break else, I will... Oh, golly. All right, I forgot my colon at the end of the else. All right, you're going to have to trust me. I wonder if I can copy and paste this mess. I'm not sure I can. Let me try it. Oh, maybe it's going to work. Print V. Yes. Yes. All right. So my for loop works because my iter and next functions work, and consequently, the for loop can do this internal while loop magic with try and except and else that it normally does. Well, that was exciting. Now let me tell you the bad news. Now that we've gotten this thing to work, I'll tell you the bad news. Okay, so these next couple of slides, 14 and 15, repeat interactively what I showed you in the code file that I have. Here's the bad news. A class really should support multiple independent operators, not just one, multiple independent iterators, not just one iterator for the class as a whole. Here's the problem with what we did. This class tuplist, you can call dunder iter to get an iterator for tuplist. But each time you call dunder iter, you get the same iterator back again, because the iterator that I'm returning here is simply a reference to the whole tuplist object itself. So for this tuplist object, the way I have defined dunder iter, I only have one iterator for the entire class. And that's not sufficient. I need to be able to have multiple independent iterators for each tuplist class object. And let me show you interactively using a list what I'm talking about. Now I need to move my interactive screen back over. When I define M to be a list of these three values, 3, 1, and 5, and I create an iterator to M called M iterator 1, I should be able to create another iterator to that same object. Here's another iterator for M, M iterator 2, and these should be completely independent of each other. So if I ask for the next value using the iterator M iterator 1, I should get a 3. And if I ask for the next value using M iterator 2, well, M iterator 2 should also start out at the 3. Cool. So M iterator 1 appears, at least so far as I can tell at this point, to be independent. And if I say next M iterator 2, next M iterator 2, next M iterator 2. Okay, cool. I was able to use M iterator 2 to step through the 3, the 1, and the 5. Remember, those are the values contained within the list M. And the fourth time I try to use next on M iterator 2, I get my stop iteration exception. But I still have this perfectly valid iterator for M called M iterator 1. Let's remind ourselves what M contains. So M contains 3, 1, and 5. I already called next once on M iterator 1 and got the 3. If I call next again on M iterator 1, this time I should get the 1. And if I call next again on M iterator 1, I should get the 5. And that's it. If I call next again on M iterator 1, now I'm going to get stop iteration exceptions. And that will be true for both of these iterators now. Unless I redefine m iterator 1 to start over as a brand new iterator for m. Okay, so I can restart my m iterator 1 over again by re-invoking my iter method on m and assigning the value I get to this m iterator 1 or MIT1 variable. Our tup list class is not this clever. So if I say TL2 gets a tup list, and let's construct this from hello, TL2 internally is represented as a tuple of 5 one-character strings, all right, H, E, L, L, and O. And when I print TL2, I get told this thing is a tup list, and it contains these 5 characters, H, E, L, L, O. When I say TL... okay, I'm not... I'm just going to say iter1 gets... TL gets iter from TL2, and iter2 gets iter from TL2. These, unfortunately, are not independent iterators. They are just 2 different names for the same iterator that starts out at the beginning of my tuple. So if I ask for next of iter1, I'm going to get the H. But if I ask for next of iter2, I'm not going to get the H, I'm going to get the E. And so forth. So if I ask for next from iter1 now, I'm going to get the first L. And if I ask for next from, well, let's say iter1, I get the second L. If I ask for next of iter2, I get the O. And then regardless of which iterator I use, iter1 or iter2, I'm done, and so I'm going to get my stop iteration exception. Okay, so this is bad. We need to have smarter iterators than what we've done so far. Now, I will point out, though, and this is fascinating to me, that what I've shown you so far, if you look up online, if you Google for how to define iterators for classes in Python, almost all of the examples that I've been able to discover show you this slightly incorrect way of doing things. They show you this way of getting a single iterator for your object rather than getting multiple independent iterators. All right, so I showed you the problem with our current iterator implementation using a tup list containing a string hello. Slides 17, 18, and 19 repeat the current incorrect implementation of this tup list class and of its dunder iter and dunder next functions. So dunder iter here is returning a reference to the tup list object, not a reference to an independent tup list iterator. All right. And using a tup list containing ints rather than string, we see a similar kind of problem. All right, let's take a look at the solution to this now, starting on slide 20. Okay, so here I'm also showing slide 21, showing the actual change that we're going to make to our tup list class. What we're going to do in order to get independent iterators for tup list objects is to create a class that we're going to call underscore tup list iter within the tup list class. The dunder iter function then in the tuplist class, instead of returning a reference to the tuplist object itself, is going to return a reference to a newly allocated tuplist iter object. All right, so this way, for a given tuplist object, each time we call iter, we're going to get back a distinct, unique tuplist iter object. And then the DunderNext function, instead of being a method within the tuplist class, is going to be a method within this underscore tuplist iter class. And so the next function will be aware of this unique tuplist iter object that we've defined, that we have available for a given tuplist object. All right, I think I need to make this concrete by taking a look at the tuplist code. Most of the tuplist code, other than for this underscore tuplist iter class and moving the DunderNext function into the tuplist iter class, is not changed. Okay, so here is our revised tuplist class. And what I want to point out here is that its init function, its DunderInit function, as well as its DunderStir function and its append function, these are completely the same as they were before. Initializing a tuplist object is the same as it was. That is, we receive an iterable as our argument. We construct a tuple from that iterable, and we store that reference to that tuple in our underscore vals data attribute. For the stir function, we simply do what we did before. That is, we return the string tuplist with the internally stored tuple of values appended to the end. And to append a new value to the end of our tuplist, we're just appending that particular value as a one-item tuple to our vals tuple. All right. So for our DunderIter function, instead of returning self, all right, instead of returning just plain self, which would only enable us to have a single iterator for each tuplist object, what we're going to do is to create a brand new tuplist iter object so that each time DunderIter is called, we get back a new, unique, independent iterator for that tuplist object. And here's how that tuplist iter class works. Of course, any class has to have its own DunderInit function. And notice in this case that as an argument to the tuplist iter function, we're passing in a reference to the current tuplist object. We're saving a reference to the current tuplist object into our underscore tuplist data attribute, and we're setting the index to 0, just like we did with the previous iter function that we had implemented. All right. Now, within the tuplist iter function is where we have our DunderNext function defined, and we're comparing the iterator, the index that is within the current tuplist iterator object to the length of values associated with the overall tuple list. If the current iterator's index is within the correct range, then we can obtain the value that we want to return, increase our index, and return the appropriate value. Otherwise, as usual, the next function is supposed to raise the stop iteration exception if there are no more values to return. So let's go on and look at some example code. Now, when I create this tuplist containing 251, and I'm calling it TL1, with this revised tuplist class that has this tuplist inner class, when I create an iterator for TL1, I do get a tuplist iter object, and when I create another iter, when I call iter again for TL1, I get a different tuplist iter object. All right, so each of these is now an iterator that I can use to traverse through this tuplist object, but the two iterators are independent of each other. So if I ask for next of the first iterator, I get back the first value, which is 2. If I now ask for next of the second iterator, I also get back 2, because the second iterator was not in any way modified by using the first iterator, and so on. So these iterators are now independent of each other. Let me demonstrate this in my code window so that you can see what I'm saying here. All right, so here is our previous program, the original tuplist, which, as we saw, did not have independent operators. Now I'm going to open the new version of the tuplist. Oops, I need to shrink that so it'll fit in my window. There we go. Okay, so this version of tuplist does have a nested class, a tuplist iter, as we showed in the notes. And when I run this, I get the examples shown here on slide 23. Although, so in the case of the code in the example, we have also added 9 to the end of our tuple list, our tuplist. Let me exercise this thing interactively. I'm going to say TL2 gets a tuple list. Come on, tuplist. And let me initialize this thing with 1, 4, 2, 7. Well, that's enough. Okay. So I'm going to initialize this tuplist using a list of 4 integer values, and I'll create TL3 as a tuplist initialized from, initialized from a string. All right, so now if I print tuplist 2, I see that it's a tuplist containing 1, 4, 2, 7. And if I print TL3, it's a tuplist containing the one character strings O, K, A, and Y. Now I can create an iterator. I'm going to just call this iter 2A as an iter on TL2, and another iterator, iter 2B, on iter TL2. I claim that those two iterators both refer to the tuplist TL2, but that they are independent of each other. And now I'm going to create iterator 3A as an iterator for TL3, and iter 3B as another iterator for TL3. And those also, iterator 3A and iterator 3B, I claim are independent iterators, both referring to the tuplist TL3. So if I say next of IT2A, I should get a 1. All right, I should get a 1. And if I say next of IT2A again, I should get a 4. If I say next of IT3A, I should get an O. if I say next of IT3B, I should also get an O, right? Because I'm claiming IT3A and IT3B are independent iterators referring to this tuplist containing these 4 strings. All right, so I do get an O. All right. If I ask for next of IT2A, I should get a 2. And none of these 3 uses of IT2A should have any effect on the separate independent iterator IT2B. All right, so I can ask for next of IT2B and get a 1. I'd better print IT2 again. Whoops. TL2. TL2. I'd better print TL2 again so we remember what's in it. All right, it contains 1427. So if I say next IT2B, next IT2B, next IT2B. All right, I have now obtained the 1, 4, 2, and 7 within the tuplist TL2. And if I ask for yet the next value from that iterator, IT2B, now I'm going to get my stop iteration. But I can still get one more value out of IT2A. I can still get the 7 out of IT2A. And now I've also used up, in some sense, that iterator as well. But my iterator, IT3A, referring to the sequence of strings, OKAY, is going to give me back the K. And so forth. Okay, so with that revision, by adding that nested tuplist iter class and revising our iter function and moving the next function into the tuplist iter class, we were able to create truly independent iterators for our tuplist class. Okie doke.